When you save a file, it becomes what security professionals call data at rest. This is static information sitting dormant on a hard drive, inside a database, or on a cloud backup server. Organizations spend heavily on network defenses like firewalls, but those only protect data in transit. If an intruder bypasses physical security and walks out the door with a server or laptop, every network-based barrier is instantly bypassed. Because physical perimeters fail, the data itself has to be armed. It requires an internal layer of defense to survive when the hardware falls into the wrong hands. Imagine a server sitting in the basement of the fictional Oakwood High School. It holds thousands of highly detailed student records. That server is packed with personally identifiable information, or PII, like names, addresses, and social security numbers. It also holds protected health information, or PHI, including medical records and allergy profiles. If a thief accesses this data, it exposes every student to identity theft and medical fraud. Securing these specific types of sensitive records is a strict compliance mandate. Federal and industry regulations dictate exactly how institutions must manage the risk of storing this information. This diagram shows role-based access control, or RBAC. Enforcing the principle of least privilege, a data owner assigns access tiers, like read, write, or execute. A standard teacher logging in receives a different tier than an IT administrator, preventing them from opening administrative files. That control works perfectly when the system is running normally. But if an attacker breaks into Oakwood High and steals the physical hard drive, they bypass the operating system entirely. The access control rules disappear. Cryptography uses a mathematical algorithm and digital key to scramble readable plaintext into unreadable ciphertext. This is symmetric encryption. It uses the exact same key to lock data into ciphertext and unlock it back to plaintext. By scrambling the information, encryption guarantees confidentiality. Even holding the stolen hard drive, the thief cannot read a single student record. But symmetric encryption comes with a catch. Because that single shared key handles both encryption and decryption, anyone who finds it can read the data. Effective key management requires isolating keys and protecting them far away from the data they secure. If a key is stored on the same drive it protects, the encryption is useless. Protecting files is one thing, but user passwords require a different approach. Passwords should never be encrypted, because encryption is reversible. Instead, they must be hashed. A cryptographic hash function is a one-way, irreversible process, turning an input into a fixed-length string. Notice the top and bottom rows. Identical inputs yield the exact same output. But even minor misspellings generate completely unique hashes, demonstrating the avalanche effect. To prevent attackers from guessing these outputs using pre-computed lists, called rainbow tables, defenders use salting. They add random data to each password before hashing, making every output unique. Hashing and salting ensure that if an attacker manages to steal the user database, they receive completely unique, irreversible strings of characters. Because of this, they cannot reverse engineer the passwords. Asymmetric cryptography relies on two distinct mathematically linked keys, a public key and a private key. To create a digital signature, a sender uses their private key. The recipient verifies it with the sender's public key. A match confirms the data's integrity. While asymmetric signatures verify that data has not been secretly altered, you still have to worry about data being destroyed. Keeping encrypted, off-site backups guarantees the availability of that data when an emergency strikes. Back at our Oakwood High scenario, the attacker plugs in the stolen server. Instead of a massive payout of PII and PHI, they are staring at endless strings of unreadable code. Because the school secured its data at rest with strong cryptography, the physical theft of the hardware achieved absolutely nothing. The records remained locked. Securing stored data requires a multi-layered approach, recognizing the vulnerability of data at rest, applying role-based access control, locking files with encryption, protecting passwords with hashing and salting, and maintaining integrity and availability through signatures and backups. Take a moment to test yourself. Can you explain the difference between hashing and encryption? Why do we use salting? And how does a symmetric key differ from an asymmetric pair? Properly applied cryptography transforms vulnerable stored information into a locked state that only trusted users can comprehend.